Understanding model degrading. Model decay, aka model degrading, refers to the gradual degradation of a machine learning model's performance over time due to changes in data drifting, relationships between input and output, aka concept drift, or the emergence of previously unseen classes, features, or users' behaviors. This often results in accurate or low confidence predictions. Addressing model decay typically requires model monitoring, loop feedback analysis, and retraining or redesigning machine learning models to align with the evolving data architecture and business objectives. As you can see here, this is represent the graph, represent machine learning diagram. Starts with data digestion, data processing, ML modeling, model evaluation, then model development, model production, and feedback loop. Sometimes the feedback loop, there are some delayed in retrieving data from feedback loop, which can accelerate the model decay or model degrading. Additionally, model decay, sometimes referred to as model rot, is closely related to the concept drift in data streams as new, previously unseen classes emerge. A model might misclassify them as outliers or inappropriately adapt to them through dynamic tuning methods, such as online updates. These behaviors can significantly degrade the model's ability to generalize over time. Remember, data stream drifts due to fluctuations in users' preferences or trends or even purchases habits shifts. Maybe the problem is related to the features used to make predictions, or the ranking of the feature importance is changed, which leads that the model has poorly predictions. It becomes worse even with the machine learning model uses time series forecasting due to trends, seasonality, and stationary effects. Symptoms of model decay. Decline in model accuracy with fluctuations in bias and variance, indicating potential overfitting or underfitting in the machine learning model. It happened also due to emergence of new previously unseen classes or features values in production data, as I highlighted. Or instability in causal relationships between features and the target variable, suggesting changes in data dynamics. Mismatch between training and production data distributions, aka data drift. Model predictions consistently breach defined business KPIs or performance thresholds. Increased negative feedback, complaints, or reports of inaccuracy from users. Things to consider when we talk about model decay. Avoid naive fine-tuning on the new data streams. Don't try to fix your machine learning model by using hyperparameter tuning. First, analyze data fluctuations to detect potential drift, then apply suitable strategies like incremental learning or transfer learning or even regularization technique to ensure model stability and adaptability. Outliers may represent previously unseen patterns or even new unlabeled classes. Instead of discarding them, consider using clustering or anomaly detection to assess their significance. Properly handling these outliers can enhance model generalization and uncover valuable insights. And finally, capped values can signal model degradation or shifts in data stream, often caused by changing trends or user behavior. So detecting and embracing these shifts is essential for improving recommendation systems and creating more accurate forecasting models. Of course, there are several potential solutions to prevent machine learning model degrading or decay, starting with the system monitoring. Set internal triggers, alarms, and investigating new label instances. This is critical because of the defense against model decay. Detects data drift, concept drift, and emerging patterns. Still, it's crucial to distinguish between noise data, outliers, and unseen featured classes. Noisy data represents addressed versus or addressed via denoising robust statistics or data augmentation. Outliers often retrained using as a fraud detection, but may need weighing. Unseen features classes indicate true concept drift, retraining, or new model architecture. How companies usually do that is by defining business objectives and thresholds. Then designing alerting system mechanism. Second point is regular users feedback analysis. Then A/B testing, causal inference, and explainable models. These techniques measuring the model deployment and all this analysis bridges the gap between complex models such as XGBoost and neural networks and human decision makers. Number 4, designing business objectives and business KPIs based on users' preferences and needs. So here, model decay isn't always caused by poor predictions. Sometimes degrading happens due to misalignment between users' needs and business values, which prevents the models to become technically accurate, but strategically useless. I see it a lot personally as more and more companies jumping to integrate LLMs models over prioritizing users' preferences. Maybe your users have urgent issues related to the product itself, more critical than constructing generative AI features to your website. So, a good reflective question to help you understand and potentially prevent model degrading can be, why are we building this? Who actually benefits from it? Does this align with the user feedback we have received over the last few quarters? Because model decay can be invisible to traditional business objectives and technical business metrics. A model might show great performance on paper, but still fail in real-world usage. A short memo answering these questions is more valuable than a high accuracy score if we want to build products that actually matter. And finally, designing shadow mode for production and full documentation. I will leave you with these beautiful graphs that describe the problems with the model degrading, such as outdated systems triggers, data drift, concept drift, label feedback delay, model stillness, misalignment with business objectives, monitoring gaps. And that's it for today. Thanks for watching. If you find my content useful, like this video. And I see you in the next video. Bye!